You're gonna want it after you sleep. No, I didn't sleep. Okay, well you could have, but you were to come to this class instead of watching. Yes.
Say when was YouTube? Who was the second championship round?
Yeah. Yeah, I do actually.
All right. So, on Wednesday we talked about matter, leading up to discussing the states of matter, how solids don't change their shape, whereas fluids can, implying that a solid could be submerged within a fluid. That is going to be kind of where we pick up today. The idea that when something is submerged in a fluid, the fluid's traits tend to start acting on that particular object in interesting ways. Namely, the fluid is going to exert something upon the solid called pressure. Now, again, I like talking about how the physics words that we use in this class get used in more common English, and then compare that to the science definition. So, off the top of your head, when you hear the word pressure, like used in everyday English, what sorts of places do you think do you hear it used? How would you define pressure outside of this class?
I don't know how to describe it. I just like underwater or like in a plane.
Okay. And I only pointed towards you because it looked like you were signaling.
Yeah,
I'm sorry.
just like, yeah, I don't know.
All right, yeah, so you hear about pressure as it relates to things like planes and going underwater. And that is basically the same situation as I was describing a second ago. When you go underwater, you are submerged in a fluid, and namely the water in that case, and the fluid does start exerting a pressure upon you. As well as that, when you are in an airplane, there's air outside of the plane versus the air inside of the plane, and there's kind of a pressure difference between the air inside and outside. So pressure does get brought up on airplanes a lot. Now the physics definition of pressure, to kind of just go back to describe how that word is used in those situations. The physics definition of pressure is a force exerted over some surface area. Pressure happens when a force is exerted, and specifically when that force is applied across some surface area. We've discussed forces a lot up until now, and how objects do exert force upon one another, but whenever one thing is touching another thing to deliver a force, there's always a certain surface area of contact between them. If you touch something with your hand to try to push it and exert force, the surface area in question is going to be the flat two-dimensional surface area of the palm of your hand. And that area, in conjunction with the force you're exerting, determines the pressure that you are exerting on the other object, and in turn that determines the pressure it exerts back on you. Because if you push on something, it pushes back. It's going to exert force back over the same area of your palm. So not only do you exert force on things, and therefore those things exert forces back, you exert pressure on things, and it will in turn exert pressure back. So kind of discussing Newton's third law still as well. And most forces that you experience are actually delivered via pressure. Because most contact forces, anytime that something is physically touching one other entity and imparting force into it, that tends to happen over some applied surface area. Any contact force, a force requiring the two objects to be physically in contact with one another, like normal force from the table, or just any time you use your hands to lift something, that force is always applied over some amount of surface area. And so the definition of pressure is, again, force over area. You take the force that you're exerting, you divide it by the cross-sectional area that you are exerting it over, and that tells you pressure. The capital P here is pressure, F is still force, and A is the surface area that force is being measured over. In physics, we like to use units of pascals for pressure. It's just a very specific metric unit for pressure. Whoops. For context, 1 Pascal is equal to 1 Newton of force exerted over a 1 meter squared surface area. For scale, that is about 1 meter squared of surface area, and 1 Pascal is equal to 1 Newton of pressure, 1 Newton of force, exerted over this entire thing. Only 1 Newton pressing into this entire flat area. So 1 Pascal is really teeny tiny. It's not a whole lot of pressure. For context, atmospheric pressure on this planet I mentioned that 1 Pascal is teeny tiny. Air pressure on this planet right now is 101,325 pascals. That's the air pressure you are currently under. 1 Pascal is not a whole lot. So again, just scale building. There's another unit for pressure though that you might be more familiar with, and that is pounds per square inch, alternatively called PSI. It's just different unit of force, different unit of area, so the imperial unit instead of the metric one. And basically anytime you have ever exerted force with your own body, it has been via pressure. Bless you. Because again, anytime you touch something, there's only a certain finite surface area of contact between you and whatever you are touching to exert force upon. If you are using your whole hand, the area would be the flat area of your whole hand. If you are only using one finger, it would just be the flat area of your fingertip. And as it turns out, the human body's kind of weird, especially in the way that we sense things, our nervous system. You don't actually have any nerves that detect force, technically speaking. You have no nerve endings that are built to detect force. And I know this because you don't really feel the force of gravity acting on you. All you really feel is the ground pushing up against you most of the time. That's why if you feel weightless when you are falling. You're not really weightless, you just feel like you're weightless because the ground isn't pushing up underneath you. So human nerves can't detect force. What human nerves actually detect is pressure. Because there's the force of gravity acting on you right now. That doesn't really exert pressure because it's not really applied over a surface area. Gravity's not a contact force. But what is a contact force is the normal force on your feet. That acts on the flat surface area of your feet. So just touching your own arm, that's a contact force. And that means that there is a surface area that that force is exerted over. Therefore, what your nerve endings are really feeling is pressure. I'll elaborate that a little bit more in a second. But for right now, this is our formula for pressure. Pressure is force over area. How are we feeling so far? Okay. I'm going to write that formula up so you still have it when I tab away from this slide. P equals FA. And we're going to do some light numerical calculating just to gauge a few things about this particular formula. Let's say that, again for context, Let's say we exert 1 Newton of force over a 1 meter squared area, again, over that whole square I had up here a second ago. Just 1 Newton of force. This formula would tell us that F over A, 1 over 1, that situation would be 1 Pascal of pressure, which again, is not a lot. Now let's say you take that same meters squared of surface area and you double the force you're exerting on it. What happens to the pressure? Plug in double the force, what happens to my answer?
2 times bigger.
2 times bigger, yes. So the relationship between force and pressure is a direct correlation based on the way this formula works. If you increase the force, you increase the pressure. And that's why at high pressures, you tend to feel you have more force acting on you. And that's why going into literally high pressure environments like the bottom of the ocean has a lot of forces involved trying to compress your submarine. Now, alternatively, let's say I keep force the same, but I cut the surface area in half. I keep force the same, but I am instead exerting the same force over a smaller surface area. What happens then? Yeah, why can't I speak today? If you cut the surface area in half but keep the force the same, the pressure still doubles. You're dividing by a smaller number, so you get a bigger answer. So pressure is, like it's here in the formula, pressure is determined not only by force but also by surface area. And if you reduce the surface area that a force is acting on, you increase the pressure that you get. I mentioned a second ago that the human nervous system doesn't detect force. The human nervous system only detects pressure. And I can prove it. Let's say that, to kind of test this hypothesis, you take the whole flat of your hand and you press down on the table. You exert a certain amount of force, and that force is spread across the area of the flat of your hand. So there's a certain amount of pressure right now between you and the table. You're putting pressure into it, it's putting pressure onto you. Get a base feeling for how much pressure that is. And now, to change things up slightly, we're going to reduce the area that force is exerted over. We're going to switch from pressing down with our whole hand to just one fingertip. I want you to press down with about the same amount of force, and I want you to tell me if that hurts more. You don't actually have to do it if you want to. You've probably done something like this before. Same amount of force suddenly hurts more if you're only using your one finger. It's kind of hard to even keep your fingers straight to be able to try to do this in my experience. And that is because simply this area is less than this area. Therefore, when you exert that same amount of force with only your fingertip, the pressure rises because the area is so much smaller. And the pressure is what you're actually feeling. This relates to something called the bed of nails scenario. A single nail has a really tiny surface area, like the tip of that nail has minuscule surface area. So sharp objects tend to actually generate high amounts of pressure because their surface area is teeny tiny. Divide by a teeny tiny number, you get a lot of pressure. Doesn't even take a whole lot of force. That's why humans invented needles for medical purposes. It doesn't take a lot of force to generate a lot of pressure with a pointy object. And so if you sat on one nail, things wouldn't go so high. But if you sat on a lot of nails, like even if it's just 10 nails, that's 10 times the surface area, and therefore 10 times less pressure, and you're less likely to hurt yourself. So if at any point in media or some sort of cultural scenario you've seen someone sitting on a bed of nails, the fact that it's a flat bed of nails instead of one nail is the reason why this is possible. Multiplying the surface area cuts down the pressure, and pressure is what actually hurts you. Is that all right so far? All right. Now, that's mostly talking about pressure from objects in the world around you. Now I want to relate this to the air pressure that I've been hinting at for a while now. I've mentioned that standard atmospheric sea level air pressure is 101,325 pascals. Barring any weird variances due to weather conditions, this should be the air pressure currently acting on your body. 1 Pascal is 1 Newton of force exerted over a 1 meter squared surface area. So right now, this pressure is acting on the surface area of your body. Now, humans aren't a standard geometric shape. We all have very different surface areas. But if you went out of your way to try to calculate the surface area of a human, you could do that. There are ways you could calculate that. And after some cursory math, I've evaluated my own surface area to be about 2 meters squared. Kind of rounding to 2 just for simplicity's sake. So just using myself as an example here, how much force does the atmosphere exert on my body if my surface area is 2 meters squared? How much force is the atmosphere exerting on me right now? Pressure equals force over area. So I'll plug in atmospheric pressure. I'm going to solve for force, plug in my surface area of 2 meters squared. To solve for force, we need to multiply both sides by 2. So 2 times 101,325 equals force. And so the amount of force from the atmosphere currently acting on my body is 202,650 newtons. Does that sound somewhat incredible? Meaning unbelievable. Like, do you believe that? It's okay if you don't. Honest question. Like, does that sound like the amount of force that the atmosphere is currently using on my body? Okay, some people are not. Sorry?
What happens when it changes to really low over time? What do you do to
Good question. To kind of quickly answer them, if the pressure becomes too much, you get crushed, and if the pressure becomes too little, you explode. So basically, what happens if you were on the seafloor, you get crushed, versus if you're in space, you explode. That's the quick example. That's the quick explanation. So that is currently, approximately, the amount of force that the atmosphere is exerting on me. I don't notice it, thankfully. I have never been able to pay attention or consciously be aware of that much force, which is a good thing. If you could feel it, you'd be driven insane. I now want to explain how that works and why the number is that big. Because even if you don't have the same surface area as me, even if your surface area is only half as much, well, that force only goes down by half. It's still hundreds of thousands of newtons acting on you that you aren't consciously aware of. So I want to discuss why that works, how this happens. This is not a scale drawing. I want to make that clear. Very out of scale here. This is you on planet Earth. So Earth, you, and at all times on this planet, you are surrounded by Earth's atmosphere. If you zoom out to look at Earth from space, you don't usually see the atmosphere because air is transparent, so I've colored it in blue to be able to see it. And as long as you're on planet Earth, you are at all times surrounded by that bubble of air. Now, the reason that Earth has an atmosphere is because of gravity. The atmosphere is made of air. Air is made up of molecules, right? You're breathing in mostly O2, some nitrogen, you're exhaling CO2, so that's still in the room with you. So the air is made up of molecules of various elements and compounds, right? Molecules have mass because they're made of protons, neutrons, and electrons that have mass, correct? So that means that air has mass, and that means that air has weight. The atmosphere weighs something, and that means that Earth's gravity is pulling on the atmosphere, trying to keep it pressed down to the planet. If the air didn't weigh anything, there'd be nothing keeping it on the planet. The only reason we have this atmosphere here is because Earth's gravity is keeping it here, and that's why it's also shaped like a bubble. But because the air has weight, all the air that's above you, the entire several mile high column of air above you up until you exit Earth's atmosphere, is literally pressing down on you at all times and crushing you. So all of the air that's above you is being pressed down on top of your head at all times. And that's why if you go up on top of a mountain, air pressure drops, because up on a mountain there's less air above you. As you elevate, there's just less atmosphere above you whose weight is bearing down on you. So air pressure does drop when you scale a mountain, or when you get on a hot air balloon, or when you're on a plane. So increase elevation, decrease air pressure, because there's less atmosphere above you weighing down on top of you. Now when you stay on the surface, all that atmosphere is crushing you downwards, so you'd think that you'd feel a massive downward force on you at all times. But that's not technically true, because the air isn't only above us, it's also surrounding us on all sides. You are submerged in air. You are swimming in air right now. So not only is there air pushing down from the top, there's also air pushing in on your sides, and also technically up from underneath too. There's also the ground pushing up from underneath, thankfully. So the net force from this pressure doesn't only point down, it pushes in all directions, because that's what pressure does. Pressure always exerts force either perpendicularly into or out of the surface area it's acting on. We're kind of back to normal force again. Air pressure will always point inward on your flat surface area. So inward on all sides, all those different force arrows just kind of cancel out. There's not really a net force in one direction. So the atmosphere isn't really crushing me downwards, it's crushing me inwards. First of all, does that make sense? Okay, so it's crushing inwards, and that's why you're not just being literally pancaked by the column of air above you. Now that said, you are still being crushed inwards, which you'd think you'd feel that as well. If you crush a soda can inwards, it compresses and collapses, right? So there's a reason you're still not consciously sensing the air pressure. It's because your body is designed around it. The human body, as well as everything that lives on the surface of this planet. magnet is specifically designed and calibrated to deal with this pressure and the force that it brings with it. You don't notice it because it's just part of you. Your operating system is designed with it in mind. In fact, your body kind of requires this much air pressure. Again, not a biologist, but in studying the physics of this, I have learned that one of the mechanisms your body uses to deal with this constant inward squeezing is to constantly push outward via your blood flow. You have pumping blood that is constantly circulating through your body, and that means that the coursing blood in your veins and arteries is pushing out against the air pressure. And so what your blood flow is doing is equalizing the pressure against what is coming in from outside. Your blood flow pushes out, the air pushes in, so you're constantly neutral and you don't notice anything because the net pressure is zero. You only really notice air pressure when it changes. If you go up on a mountain, less air above you, air pressure drops, that's when things start getting weird. That's when your ears pop. It's when you start not feeling quite right. And that's because your blood flow needs time to equalize to the new pressure and adequately exert the right pressure back while also circulating oxygen throughout your whole body. It's also why if you go down to the bottom of the ocean, your blood can't create enough pressure to overcome the increased pressure from the water, and at best you get the bends, at worst you. So, you don't notice this because you're built around it and you need it. If you're in an environment with too much pressure like the bottom of the ocean, you get crushed. If you leave the atmosphere entirely, your body doesn't know to turn off blood flow to stop exerting the outward pressure needed. Like, your body's gonna pump blood as long as you're alive. So if you just suddenly pop this person out here where there's no atmosphere, their blood doesn't stop pumping, so they keep pressing outwards to counteract an air pressure that isn't there anymore. And that's why in movies, if someone gets thrown into space, they explode. Literally, your body would tear itself apart because you can't turn off that outward pressure. We are built to have that outward pressure to counteract the inward air pressure. So space is dangerous. Important thing to note, you don't explode in space because space tears you apart. You explode in space because your body tears itself apart. The vacuum doesn't do anything. What does something is your body not being able to adequately exist in a vacuum. How does all that horror story stuff sound? Makes sense at least? Okay, so the atmosphere is important. We need it. And because we like math in this class, I'm going to show you how we calculated atmospheric air pressure. Because there's a formula for it. This formula is how you calculate fluid pressure in general. This is the pressure from being submerged in any fluid. Right now you're submerged in air, so we could use this to calculate air pressure. But you could use the same formula to calculate water pressure if you were instead submerged in water. Any fluid, you can use this formula to figure out the pressure it would exert onto you if you were in that fluid rather than or including air. So, new formula. Fluid pressure is equal to the density of the fluid times the strength of gravity on this planet. I've put absolute value brackets around it because this formula doesn't want a negative sign that's usually on G. So if you plug in -10, the absolute value brackets get rid of the negative and make it positive. So this is a formula that doesn't care about the negative because vector math gets rid of it. It just cares about how strong gravity is on this planet. So fluid density times strength of gravity times the depth that you are within that fluid. Basically how much fluid is above you pushing down on you to create the pressure. we were calculating air pressure, that depth would be the height of air above your head. So, you know, the miles of atmosphere up until the edge of it. If you were instead swimming in water, like if you had gotten yourself down to the bottom of a swimming pool, depth would be just the column of water above your head. So when I say depth, it's the height of water from you, from object, up until the edge of that fluid. And you can use this to determine the fluid pressure of any fluid that you can be submerged in, as long as you know the density of that fluid and how deep you are in it. Questions so far? All right, so this is just the math that explains the, this visual. We are this deep in atmosphere. The density of the atmosphere in conjunction with that column of air is what creates the 101,325 pascals of air pressure that exist on the surface of this planet. And that's also why, again, if you go higher up in elevation, if you were instead on top of a mountain, there's less air above you. So you plug in a smaller depth, you get less air pressure on top of a mountain. All sound good so far? Okay. This is a new formula. I want to run a small number of one or two quick calculations, and we'll call it for the weekend. I talked about how the air pressure number was calculated from this, but I want to run through quickly how we could do water pressure as well. Let's say that you are 3 meters under water in a freshwater pool. So, it's pool day, tank of fresh water, and you have gotten yourself all the way down to the very bottom of that swimming pool. At least when I was a kid, me and my cousins would all try to play the game of who can get down to the bottom of the pool and stay there longest. I wasn't the only one, was I? Okay, cool. So let's say we're playing that game 3 meters down, that's about a 10-foot pool. So my first question is, since the density of fresh water is 1,000 kilograms per meter squared, what will the water pressure be at that depth? Formula says fluid pressure equals fluid density times the strength of gravity times the depth of the fluid. So we'll plug in the density of fresh water. We will plug in the strength of the gravity. Again, it doesn't want the negative sign. Put the absolute value brackets in there. And we are 3 meters down. So the water pressure, I'll be more specific here. Pressure water, 1,000 times 10 times 3, so 30 times 1,000, 30,000 pascals. And that is just the water pressure. First calculation sound okay? Okay. Now, couple small tweaks we're going to make to this number. First of all, just something that you should know about living on this planet. This is what the water is going to do to you at this depth. But going underwater does not get rid of air pressure. I want to make that clear. If you think you can escape air pressure by going underwater, you can't. Because the air is also pushing down on the surface of the water. And therefore, the air pushing on the water causes the water to push harder on you. So going underwater does not get rid of the 101,325 pascals. This number just gets added to it if you wanted to calculate the total true pressure on your body. A lot of scientists just kind of zero out the atmospheric pressure because you're used to it, and they only start calculating about what is added to it. So this number is what is added to the pressure going on your body when you're down here. Does that make sense? If you did ever want to calculate the true pressure, which is the term scientists tend to use for the total amount of pressure on your body, including atmosphere and everything else, you would just add all of it together. So we would just add the 30,000 into the standard atmospheric number. And by going 3 meters underwater, you've about increased the pressure on your body by 30%. So if you went 10 meters down, you double the pressure on your body, that being about 33 feet underwater. And this is again why deep sea divers have to be very, very careful. So that's the true pressure. It's just we're adding the water pressure to what is happening to our bodies. Just that makes sense? All right. Now, last couple quick concepts. What happens to just the water pressure if you go twice as far down? Doubles. Yes, not a trick. If you go twice as deep, if we put in 6 here, we get 60,000. So the water pressure would double, and then we would add the doubled water pressure to the air pressure to find the true pressure. So if you are twice as deep in a fluid, that will increase the pressure by ×2. So again, be careful when deep sea diving. And lastly, I want to point out that salt water is denser than fresh water. Salt water has a higher density than fresh water because there's something dissolved in the salt water. There's physically more matter contained within the salt water. There's literally salt dissolved into it. Does that make sense? So salt water is denser than fresh water. Knowing that salt water has a higher density number, is this pressure going to be bigger or smaller if you were at the bottom of a saltwater pool?
Bigger.
Bigger. Very good. The higher the density of the fluid, the more pressure it exerts. So another reason deep sea diving is dangerous, the salt water is more dense than fresh water, so sea pressure is going to be way bigger inherently than the pressure at the same depth of a lake, for instance. But furthermore, again, fluid density directly contributes to the fluid pressure. And that's one reason why you don't really notice air pressure. Air doesn't have a big density. So you're used to it, it doesn't interfere much. Water, 1,000 times, at least more than 1,000 times more dense than air. And so water pressure starts adding up a lot faster than air pressure does. Make sense? All right. I suppose if you wanted the most dense, you could swim in syrup, also mercury, but that's a bad idea for a different reason. Any questions before the weekend? All right, let me know if you need anything, and next week we're going to talk about how all of this causes floating. So let me know if you need anything over the weekend. Have a great weekend, rest well. That's it. See you guys.